PV graph, I summon you again. I need you to destroy the world. Okay, so we're looking at a PV graph in our notes. And in this PV graph, we're looking for three things. We're finding the temperature at each vertex of the graph, the change of internal energy over each of the process, and then how much work is done for each process. And then we'll actually use that to find the total work done in the graph. We actually don't have numbers here. Everything is in terms of P naught and V naught, which is kind of a pain. And we'll be able to derive a T naught here, which, while that is a little bit of a pain, it's actually, in my opinion, nicer than dealing with numbers because I hate this thing. It's the worst. So let's start for part A, as I unfreeze my screen. Let's start for part A here of finding the temperature at each vertex. And the vertexes are A, B, and C. C is in kangaroo. Now, in order to find the temperature, what we really need to do, because this is an ideal gas, is we need to use the ideal gas law, Pivnert. PV equals nRT. Now, you might ask the question, how many moles do we have in this problem? But we're actually going to first initially solve for T naught and just put everything in terms of that. So if we had numbers, we would need the number of moles. Right now, it doesn't matter. So if we want to find this temperature in general will just be PV divided by nR. And if we look at vector A, or vertex A, excuse me, that's at P naught and V naught. So all we're going to have here for our T naught temperature, well, it's just P naught times V naught over nR. And this is our temperature at vertex A. If we want the temperature at vertex B, if we take a look at the graph here, we're still at P naught going across here to the right. That was an isobaric function, so a constant pressure. So we have P naught, but our volume has changed. Note our volume here is 4 V naught, and then we divide by nR. Well, the P naught, V naught, and an R are the exact same. So those are all equal to T naught, but we have an extra 4 here. So we can say the temperature at B is just 4 T naught, which is actually 4 times the temperature of A. In general, what we can see on a pressure volume graph is as we move up and to the right, temperature increases. For our last point, vertex C, our P naught has actually changed. We've become 1/2 P naught. So we get a 1/2 P naught here, multiplied by the same volume, 4 V naught, and then divided by the nR once again. The P naught V naught over nR is going to give us a T naught. The 4 over 2 becomes 2. So we get 2 T naught here, or 2 of the temperature at vertex A. So that's how we can find our different temperatures here. And if we did have numbers here, if we actually had numbers on this graph, we could just slam those numbers in with a calculator and get some value of a temperature. But in this case, we're just solving for everything in terms of constant values. Okay, so for number B, we're looking for the change of internal energy. And what we're actually doing in part B is we're looking at the change of internal energy from vertex A to B, B to C, C to A. So for each of these, we are looking for some change of internal energy. And let's pretend here that we have a monatomic gas. If we want to find this change of internal energy, we might initially think first law of thermodynamics, Q plus W. But if we just pause for a second, we will hopefully recognize that delta U also equals 3/2 for a monatomic gas, nR delta T. And we have the delta T's. We just solved for the temperature at each vertex, so we can use those temperatures at each vertex. So in doing this, if we wanted what the change of internal energy was from A to B, remember this is final minus initial, so we're actually putting the B temperature first minus the A temperature. We're going to have 3/2 N R, and then this is going to be the temperature at B, which is 4 T naught, minus temperature at A, which is just T naught. Now, if you're fine with just leaving things in terms of these T naughts, then so be it. You could end it there. But if you're like, wait a second, T naught was a derived quantity, we should really put these back into P naughts and V naughts, then let's go ahead and do that. What we would have then is 3/2 NR, and then we'd have here 4 P naught V naught over NR minus P naught V naught over NR. One of the nice things we see here is that the NR doesn't actually matter. So I didn't actually care how many moles of gas I had here. We could say that 4 P naught V naught minus 1 P naught V naught is 3 P naught V naught. 3 times 3 is 9. So we could say this would be like 9/2 P naught V naught for the delta U of A to B. And that's if you wanted to put it back into those original units. If you're like, hey, I'm just going to leave it in T naughts, then you're fine up here. Okay? So let's do this now for B to C, and then C back to A. It's going to be the same process, same exact steps. Going from B to C, we're going to have 3/2 NR, which we know we're going to cancel out in a second once we do our little math. But we're going to have, for our final here, going to C, that was 2 T naught, which we'll just write it as P naught V naught over NR, minus the initial position, which was B, because it's always, remember, final minus initial. So that's our 4 T naught, which is just P naught V naught over NR. The NR's wipe, and it wipes on both because that's a distributive property of multiplication there. What we have here is 2 minus 4 is -2. Interesting enough, the -2 here will actually be divided out with that 2 down there. And we're going to get here just -3 P naught V naught. Going from B to C. Now this is very interesting here, because going from B to C, that was an isochoric function, or an isovolumetric. It was straight down. The volume didn't change. No work was done. But yet, our delta U, our change of internal energy, was still negative. That means that somehow energy was taken out of our ideal gas. This could have happened because maybe the vessel containing our ideal gas, maybe it was put into an ice bath. Maybe after a long time, heat was able to leach from that container, from that vessel. So in this case here, for an isochoric or an isovolumetric, even though the work was equal to 0 here, for an isochoric isovolumetric, the delta U is equal to Q. Some heat was lost from our system, resulting in that delta U, resulting in that temperature change. So that's what's going on, going from B to C. Our temperature changed, but no work was done. There had to be some heat exiting our system, or if it went up, entering into our system. Lastly, if we were on the delta U from C back to A, we're going to get the 3/2 NR once again. T naught for our final position was actually P naught V naught over NR minus, and then the C position was 2 P naught V naught over NR. Third time's the char, the NRs go away. 1 P naught V naught minus 2 P naught V naught gives us a 1 P naught V naught, which would be negative here, which means that our delta U from C to A is going to be negative 3/2 P naught V naught.
Why negative?
So the question was just asked why negative. It's because here we have a 1 minus 2, which gives us -1, which then multiplies out here. So there it is. Now looking at this, we could actually look at the entire cycle. What would our delta U be if we started at vertex A and rolled all the way back around and ended at vertex A? If we wanted to do the math, we could add all of our delta U's together. We could take 9/2 minus 3 minus 3/2, and we'd get a number. Or we could take the quick and easy way out. The temperature at vertex A is T naught. When we come back to vertex A, the temperature is still T naught. The change in temperature is 0. So if we went around the horn, the change of energy going from A to A, that's 3/2 NR delta T. If that delta T is 0, there is no change of internal energy. Now, a fascinating thing about this is that if there is no change of internal energy here, we could write the equation 0 equals Q plus W, which implies in this case for a full cycle that Q is just equal to the opposite of whatever work was done. So once again, we see heat having to enter or leave the system. This is an important little piece here, recognizing that oftentimes we're asked, going around the system, what's our change of internal energy? It's nothing. Has work been done? Absolutely. There are areas that we can see in this PV graph, which we'll be looking at in a moment. So while work has been done, no change of internal energy has taken place going from A back to A. For part C, we are actually looking at the work, and we're going to do this for each process. We're going to find the work going from A to B, B to C, and then C back to A. And since these are all nice straight lines, we'll be able to do this with basic geometry. We'll also just say, what is the total work done here for this? So if we want to find the work done going from A to B, we know that the work is just an area underneath the curve. So if here's our curve up here, here's our curve, we want the area just underneath it. So we want this entire pink region right there. To get this, we need to say, what is our pressure here? Well, our pressure going from 0 up to the line is P naught. So that's kind of our height. And now we need to multiply it by the length or the width of this rectangle. Be careful here. People often put 4V naught. But 4V naught is not the width here. The width is 3. We ended at 4V naught, but we began at 1. The difference there is 3V naught. So our total work that we've done here is these values multiplied, because that is the entire area of this rectangle. That's just 3 P naught V naught. To find the work going from vertex B to C, well, we have a vertical line going down here. That's our spaghetti. So because this is a vertical strand of spaghetti from B to C, it has no area underneath it. It's just a vertical line. This is just, whoop, 0. There's no area there. I can't create an area under that curve. So we get nothing. And lastly, if we're looking for the area from C to A, coming up this red line, we have here some weird trapezoidal shape. If you happen to remember the equation of a trapezoid, you can go ahead and use it. If you're like, I don't remember that, well, neither do I. maybe it's easiest then to just do the following. We have a lovely rectangle under here that we can find the area of. That's just 3v0 times 1/2 p0. So there's 1/2 p0 times 3v0. That's our rectangle. And we'll just add it to this triangle up top. When we have this triangle, that's going to be 1/2 base times height. So 1/2. Our base here going across is the 3v0 again. And our height here, we want to be careful. It's not p0. It's the difference between 1/2 p0 and p0. So this is going to be a 1/2 p0 again. If we put all this together, we're going to get a 3/2 p0 v0 plus, and in this case here, this is going to be like 3/4 p0 v0, which really makes this close to 6/4 p0 v0, which we can then say is 9/4 p0 v0, just putting everything together. Now, one of the things that you might be looking at or confused about when we're looking at our three work values for work AB, work BC, and then work CA, specifically the A, B, and CA, is when we looked at A and B, or the cycle A to B going to the right, we've previously said that that is a negative work. So if we actually were using this in an equation where we had the first law, delta U equals Q plus W, that would be a negative. And down here, this C to A, as we're going to the left, we would call that positive. Now, some people use a different convention. They say delta U equals Q minus W. That's not what we're using, but it's still a convention that works. In that case, they would have called this positive, and they would have called the CA cycle negative. So what should you do if you're asked, is this a positive or negative value on a test? Because both are right. Well, a foolproof way of always having the correct thing is stating the following. We're calling this work negative, but we're calling this work negative because work is done by the system. Work is done by the system. The gas had some internal energy. It increased the volume out, and in doing so, it did work. The system did work. Work was done by the system. In our other case here, work is done on the system. These conventions of saying by the system or on the system, they are the exact same no matter which convention for signs that you're using. The Q minus W or our Q plus W. So what I highly encourage you to do if you're taking an AP test or if you're taking a test in college, instead of just putting positive and negatives, put your positive and negatives because, you know, we need to make sure our numbers are correct and they're going to pan out later on for our first law. But next to it, just write the three words, by the system, or work is done by the system, if you want to be a little longer, or on the system. Because that right there universally dictates what is happening with these thermodynamic processes and where that work is where it's coming from. Okay? So that's very important there. Lastly, if you wanted to find the total work done by the system, you could just add all of these up. There's nothing wrong with that, except the fact that 3 or negative 3 plus 9 over 4 is kind of weird to do. Actually, it's not really that bad to do. You know, there's common denominators or whatnot. You'd get 3 over 4 in the end. But a quicker way to do it is to simply come back here and look at our diagram. We know that the total work done by the system is just going to be the area that is enclosed by the full cycle, which in our case here is another triangle, which is pretty nice. So this triangle, if we take the 1/2 base times height, we have 1/2, our base is 3v0, and our height here from 1/2 p0 to p0 is 1/2 p0, which we actually did this as a piece of our trapezoid last, and we quickly find that this is 3 p0 v0 over 4. So our total work, if we were to add all these up, It's just that area on the inside. It is that 3/4 P naught V naught. And since we do see this as a heat engine, we're going around clockwise with our cycles. We quickly see that this will be technically a negative value. So that is our negative value, and if we wanted to be just the best, we could say this is work done by the system. So there we have it. An entire PV graph that we've worked everything out for. We found the temperatures at all the vertex. We found the change of internal energies using those differences in temperatures. And looking at areas, we were able to find the work that was done by each cycle and then the total work done throughout the system. So these PV graphs, there's a ton of information stored into them. There's a lot to pick out of them, but they are very, very powerful as a result. And we're going to be using them for our first law of thermodynamics moving forward. Until those next examples, we are finished here. And until next time, adios, and take it easy.